The original goal for this research was really to try to understand how these interesting snakes, venomous sidewinding rattlesnakes, are able to achieve their incredible locomotion using a peculiar kind of locomotion, sidewinding, on a variety of granular sand terrain. We essentially constructed a facility down at Zoo Atlanta in collaboration with Dr. Joe Mendelson, curator at Zoo Atlanta, to create basically a simulated sand dune test apparatus.
It's been known for centuries that Sidewinder rattlesnakes have this unique ability to move across sand, which is, if you think of walking on a beach, is a remarkably difficult thing to do. And it's been relatively well characterized, but not in a modern sense and not from the perspective of the sand.
We started with animal studies. We started looking at how snakes do sidewinding on sand. Once we realized they use this control template, they control the contact length, they basically increase it from 0 to 20 degrees by 41%. And that's how they successfully climb up the hill.
We got in contact with collaborators at Carnegie Mellon University, Professor Howie Choset's group there, who had a robot called a mod snake, and it turned out they had actually been using the sidewinding gait in their robot for many years to traverse all kinds of ground, but always had trouble on sandy dune inclines.
Robots are expensive, and a robot gets stuck in the sand, that's a problem, especially if that sand happens to be, say, on another planet.
That's why we started studying sidewinding locomotion of snakes to understand how they move on sand and try to transfer what we learned from biology to the robotics world.
We're really at the tip of the iceberg here because we found a really fascinating system where the snake informs what the robot can do, and then we can manipulate the robot to do the things that either the snake won't do or can't do.
So we learned, in this case, biology, physics of complex materials, as well as helped our engineering collaborators develop better robots.